Okay. The GeoAI driven spatiotemporal process understanding and prediction. So today, it's the second webinar of this series. It's our pleasure and honor to have Dr. Manzhu Yu, and who is an assistant professor at the Penn State University. And she will talk about spatiotemporal methodology for the analysis and prediction of extreme weather-related events. And before she starts, I'd like to just briefly introduce Dr. Yu. So Dr. Yu right now is an assistant professor at Penn State, and she received her bachelor degree in remote sensing from Wuhan University, and her doctoral degree in Earth System and Geoinformation Science from George Mason University. And she is a co-principal investigator of the NSF-funded Spatiotemporal Innovation Center, jointly operated at the George Mason University and Harvard University. She has recently also awarded the 2022 Miller Faculty Fellow Award at the Penn State University. And Dr. Yu's research is very active and also expert in the GeoAI. So without further ado, let's welcome Dr. Yu. Yeah, the floor is yours, Manzhu.
Thank you, Dr. Gao. So I'm really happy to speak to the community of CPGIS about my work. This is actually the first time. So value the opportunity. Please, when you have any feedback or comments, suggestions, please contact me or leave me in the chat. Thanks. So I would like to shift your attention to the cases of this year. So we all experience a very dramatic year in terms of extreme weather, and you probably, depending on where you live, you will probably experience the extreme wildfire smoke, either in the Eastern United States, Mid-Atlantic, Midwest, or the Western United States. You'll probably also experience some abnormal flooding if you're living in the Western United States. So a tropical cyclone, which is very rare in the Western coast. So this year is absolutely abnormal, and it is related to climate change. A lot of the conclusions from Science and Nature are saying that these are climate change or global warming induced extreme weather events. In many parts of the world that we can see some of the bizarre events. This is actually a infrastructure failure, so it's a dam failure in Libya. This is that in Europe, the extreme heat and people's tolerance of extreme heat is being increased, actually. And of course, the extreme wildfire this year. So comparing to the recent years, like the recent 5 years, it is still very exceptional. The highest speed, it is actually the hottest July on record. And you can see the humidity compared in the co-occurrence with humidity and high temperature are actually existing in the Middle East region, the Mediterranean region, and the United States or the Northern America. So these has been very common this 2 years. And this year especially, it is the combination between heat and humidity, which is reaching to a deadly level. So Canadian wildfire, it is because of the global temperature increase. And this is the worst ever season. Canada has doubled its wildfire emission. And this is the record by a forecast model from the European Copernicus modeling service. And outside Canada, Greece recorded its most intense burst of wildfire emission ever this year. And in the Pacific, in Hawaii, the picture that we saw became the deadliest US wildfire in more than a century. You've also probably see this in many news articles. This is New York in June the 8th this year, which is a wildfire smoke. So it's a long transport wildfire smoke, basically from Quebec, Canada. There are other cases in the Western Canada that we also receive in the East Coast. So in September 2023, which is this month, the Pacific Northwest is also having the same effect for the Western United States. So we see similar types of haze in the sky, depending on where you live. So some of the things that we probably experience based on our experience and the living experience especially, we can somehow sense that the era of extreme weather has come. So the researchers of mine are really to prepare for the age of extreme weather, even it is before we experience such dramatic cases of different types of extreme weather in such a year. So the core of my research is to develop spatial temporal methodologies in the broader field of geographic information science to quantify the dynamics of extreme weather events, to identify the relationship of these events with other physical and social factors, and of course, to enhance the predictability in different types of advanced modeling of extreme weather events and try to improve the interpretation or the explanation of complex models. So let's talk about, probably to set up the floor, let's talk about the complexity of studying extreme weather events. I know that this group must have different types of experience studying geographical events or geographical phenomena. And let's probably link your background, link your experience to the similar type of complexities in studying extreme weather. We all have complex and heterogeneous data sets. We all are dealing with some kinds of spatial and temporal dependence. In extreme weather, we're dealing with complex spatial dependence, which means that spatial dependence is not always having the spatial decay or the distance decay. And the temporal dependence is not always in the uniform, the diurnal pattern, yearly pattern. So it has many layers of temporal dependence. Extreme weather, especially, you are seeing a lot of or more nonlinear and dynamic process at the same time. Every problem in geographic problems that we're dealing with are having these mob problem. And in extreme weather events, depending on which area you're studying, it is very hard to have the same results, to have the same statistical analysis based on how you delineate your boundary of studying extreme weather events. When you have a complex model, it is really hard to make it generalizable beyond the area or beyond your time scale, which is making the model hard to explain when you're extrapolating your model results to another region or temporal scale. If you're doing analysis of extreme weather events based on observation data, this becomes very obvious, like you have limited sample size. So the overpass of satellite, the availability, the geographical and temporal availability of ground measurements, aerial measurements, all of these are making the sample size really limited. So my study is to have a better understanding by incorporating a lot of the spatial temporal dependence in different aspects. The first one is incorporating spatial temporal autocorrelation into the models. So some people have done that, and you probably have seen deep learning models incorporating inverse distance weighting or deep learning models incorporating kernel-based weighting. All these are associated with spatial temporal autocorrelation. So it means that you are kind of embedding a statistical relationship between the observation of a variable at different location and time, and that is doable. But you need to make sure that you know or you are aware that treating autocorrelation features as additional independent input or predictors, you may have failed to explore the dynamics of the complex dependency. I'll introduce one of my examples of doing such thing, which is to extract that spatial temporal autocorrelation and embed that later in my deep learning model, and you'll see the discrepancy of that. The second case is to have a spatial temporally constrained model, which means that you are using the model to integrate both a spatial dimension and temporal dimension to study or capture spatial temporal, to capture the behavior of extreme weather events. That's possible. So there are models you might have used like conv-LSTM, the convolutional long short-term memory, or other cases where you combine spatial and temporal layers together in one model so that you capture both aspects. That's possible. The third aspect is to address the heterogeneity, the spatial and temporal heterogeneity. And if you have used geographical weighted regression, then you probably know there are geographically weighted deep learning model or geographically and temporally weighted deep learning model. They can help with capturing local variations, but sometimes especially with limited sample size, you might see overfitting a lot of the cases. The fourth aspect is really to capture the spatial temporal coherence. By coherence, I mean the systematic variation across different scales in phenomena like atmospheric phenomena, ocean phenomena, tropical cyclones, things like that. So, of course, capturing such coherence will be very helpful for you to develop a physically plausible model. But the challenge is really to capture such structure, how accurately you capture the coherent structure, and how you can handle such multi-scale variation. Those are really the challenging aspects. So in a recent review paper that me and my colleagues are doing, which is to reflect on the recent advancement of different types of deep learning models and their handling of spatial data flow, temporal data flow, spatial temporal in the same data flow, or application dependent. Some of the cases that you can see is combining spatial and temporal layers like the CNN LSTM, the conv-LSTM, the graph convolution neural network plus the recurrent, the temporal one. So all these three cases are the combination of a spatial layer plus a temporal layer or multiple layers of them. So they have the ability to constrain two aspects together in one model. The other case is the attention mechanism, which many of you have probably tried transformer or the variations of transformer or attentions attached to some of these models in the second layer. So the attention mechanisms are helpful in addressing mostly the constraint of focusing on relevant information or the availability of producing some kind of model interpretation. So that is probably helpful for generalizability. When you are explaining it quite well, you know the decision process, then you can safely extrapolate to further regions, but that's to be tested most of the time. So again, based on recent advancement, we are concluding that most of the cases in the prediction modeling of Earth system science and try to study extreme weathers are to develop some advancements or some modifications of existing architectures of deep learning, or they focus on explainability of such deep learning model, or they incorporate uncertainty and try to communicate the uncertainty quite well using the deep learning model, or trying to develop physically plausible models, which we call physics-informed or physics-guided models. And to provide a little bit of an advertisement, on October the 20th, Dr. Fa Li in the same CPGIS educational series will talk about especially wildfire, understanding the physics of wildfire and try to incorporate that into a deep learning model that is better predicting the danger of wildfire. So coming back to the three core of my research, the first one is to quantify the dynamics of extreme weather events. I'm using the case of dust storm, and on the left-hand side, you're seeing a type of dust storm called Haboob. It is in Phoenix, New Mexico, but you're seeing similar kinds of Haboob in Northern Africa, in Australia. So this kind of dust storm is really like a wall of dust sweeping across the ground. And you can hardly say that it has a hard boundary. It's not like cars or other surface objects. It is having the soft boundary like many other extreme weather events or natural phenomena. So the way to quantify the dynamics is really to understand how that types of events is evolving. And in geographic information science, we have this type of event-based database or event-guided, process-guided analysis. And this is following the same length, same direction of study, which is to extract the spatial temporal linkage between soft boundaries of dust storm. So now you can detect from one time step to the second time step, what is the merging event, splitting event, continuation of dust events. For every dust event, you are saving that entire information, like the concentration, the volume, the speed of its movement into one graph. So that if you're trying to analyze 100 years of data, in extreme weather studies, we usually try to understand for a very long term so that we can quantify if it is an extreme or not extreme cases. So this case, you can have a graph database in every graph representing one dust event. And one dust event, you are linking different objects together as node, and the linkages will be represented as edges. So with that, you can extract one of the event and try to analyze the way that it is moving, the way that its volume is changing, the way that it is from one volume to split to separate volumes and decay. So the usage of such framework or the database, the graph database for the management of extreme weather events is really to identify common patterns. That is what we do in geographic information analysis, because we want to summarize the patterns of existing historical events and try to find abnormal cases. On the left hand, you are seeing the abnormal cases in January in Northern Africa. So these are representing the trajectories of dust events. On the lower hand, you are seeing all of the trajectory available from the detected events. And on the upper ones would be the detected outliers in their direction in green. So the directions should be the other way around in January, mostly. And you're seeing in red, which is the speed anomaly. And in blue, that is the volume anomaly. On the right-hand side, you're seeing typhoon tracks, which is using the same type of framework. In a graph database, you're kind of better analyzing the historical tracks of typhoon. So assuming that this black one is your current typhoon track, and based on the analysis of existing historical typhoon tracks in other colors, you are finding the similarity scores of historical typhoon tracks and trying to predict the impact level of the new one, of the existing one. The second core of my research is really to identify the relationship between the extreme weather events with other physical and social factors. I usually separate them in two tracks, so the physical factors in one and the social factors in another. And you're seeing the physical factors in the first example. So in this case, we're trying to understand what are the physical factors that are linked to the wildfire occurrence. So we're predicting the probability for a wildfire to happen at a particular location in a future time point. So of course, the training part would be using historical wildfire occurrence. The way that we're doing in this case, if you link back to the complexity of studying extreme weather events in space-time, there was a cases that I talked about, which is to modify existing architecture. And this is exactly the case. So we modify existing architecture, which is a random forest, a very commonly used machine learning model. If you have used or have heard or learned about random forests, you probably know that it is not a spatial type of model. So it's not a spatially explicit model, meaning that when you're getting a decision-making process from the random forest model, you can hardly link that decision-making process with any geographical factor or any space or any temporal factor. So to build on random forest, we kind of have a spatial temporal sampling of training data, which means that we control the part that random forest is sampling in terms of spatial sampling and temporal sampling. So in the end, you kind of have the decision-making results, which is the probability of a wildfire to happen at a particular place, and also how that decision-making is made based on the samples that you have in terms of the spatial factor and temporal factor. The second case that I'm going to present is a social factor case. This is actually a work that we've done a couple of years ago. So this was when tweet is still providing geotag. And we were able to use that geotagged tweets to make classifications after Hurricane Sandy, Harvey, and Irma, only in the places that is being impacted by these hurricanes. So we classify tweets based on their text information into classes like casualty and damage, caution and advice, resources, people missing or found. So the major 4 cases. The thing that we did to this classification is really to incorporate environmental context, which is beyond the geotag of such tweet, we have physical model outputs, like how far is the tweet away from the storm center? What is the predicted precipitation intensity? What is the predicted wind speed and wind direction? We also have observation of these variables as well to incorporate it into the predictors of classification. And using a one-dimensional convolutional neural network that is a couple of years ago, we were able to prove that convolutional neural network is able to have a cross-event capability, meaning that we can build a knowledge base for it to be used for future cases to classify tweets or informations, geographical volunteer informations into these predefined classes. The other cases is more recent, which is, again, social factors, how we can link these extreme events or natural phenomena with social factors. And in this case, it's air pollution or wildfire-induced air pollution with human mobility. So we're calculating not the population or residence population-based exposure, but we're calculating the mobility-based exposure. So based on where you go or where people go in terms of during the day, in an hourly, monthly aggregated, hourly temporal resolution, you can quantify the dynamics of mobility-based exposure. So I'm giving 2 examples on the left and on the right in the same city, but different regions. You can see this is in Los Angeles City. On the right-hand side, it is Long Beach. On the left-hand side, it is LAX, which is the airport. So we calculate the mobility-based exposure based on visitor number at a particular place and the pollutant concentration, and in this case, it's PM 2.5. So supposing either of these factors are exceptionally high, the mobility-based exposure value would probably appear as a hotspot within that region, indicating a potential area of concern for public health or air quality. However, it is important to note that both factors, they are sometimes contradictory. They're not always high in terms of temporal dependence. So in the left-hand side, which is the airport case, you're seeing that in the area, they have a relatively low PM 2.5 concentration, but it is having a high number of visitors. On the right-hand side, you're seeing a low number of visitors, but a relatively higher PM 2.5 concentration. So in the first case, which is the left case, you're seeing the risk of exposure to PM 2.5 visitors might be low. But in the second case, the risk of visitors may be higher. So the second case, the third core of my research, which is the largest core actually, is to predict or enhance the predictability of extreme weather. And in some cases, I will be showcasing the model interpretation, some cases not. But the general focus is really to improve the decision-making process, to improve the explanation of the decision-making process within the model. So this case is to improve the urban spatial variability of extreme heat when we're experiencing urban heat island and heat waves. So we're using a data set which is having a very high spatial variation, that is the Internet of Things data, the sensors mounted on fleets within different large cities, and we're using New York as an example. So the model is really the standard of the art model for the cases when we were doing it, which is in 2020, the stacked LSTM. Sometimes in the current examples that I'm doing, LSTM is really hard to beat. So LSTM, it was the model that we use. This is really to demonstrate that with a Internet of Things data set, you kind of have the ability to train with historical data set, which we have a longer time period. So for Internet of Things data set, you might have 3-year or 5-year, but for weather stations, you have tens of years of data set. So this showcased that when you're combining a shorter term data and a longer term data trained for the same area, assuming that the spatial variability of the same area is keeping the same way, then LSTM can help us to predict short term based on the higher spatial variability of the IoT data set. The second case is I'm going to showcase that the incorporation of spatial temporal autocorrelation, which is one of the aspects, if you remember, the four aspects of incorporating spatial temporal dependence. And this is the first one that I talked about, which is incorporating spatial temporal autocorrelation. This will be that case. So the purpose of this study is really to have a higher temporal resolution of tropospheric nitrogen dioxide. From the satellite observation, we have a daily time step of tropospheric nitrogen dioxide, which is on the right-hand side, this one. This is the ground truth of our model. It is a satellite observation, satellite product, which is very helpful, daily temporal resolution. But if you want to have a temporally diurnal effect of diurnal patterns of nitrogen dioxide, you probably want to find the relationship between tropospheric nitrogen dioxide and the hourly measurements on the ground. But knowing that the ground observation and the tropospheric nitrogen dioxide, they are basically different variables, quite different, especially in the urban area where you're kind of emitting a lot of nitrogen dioxide from the ground. There are two cases that we tried out. The first case is a standard case in geographic information science, which is to incorporate a IDW, a inverse distance weighted interpolation. So a spatial interpolation, which is to help us find out the spatial autocorrelation, right? So incorporating IDW and then find out the relationship between the ground-based nitrogen dioxide and the tropospheric nitrogen dioxide using a deep neural net, which is a regular feed-forward neural net. That's the first way. The second way is to directly map the irregular location of the ground observation nitrogen dioxide towards the field, towards the map of tropospheric nitrogen dioxide. So from the input to the output, without doing any interpolation, we're directly mapping it. So this is incorporating a deep matrix layer, which is very much like a graph neural net or a variational graph convolution. But in the end, we're keeping that the same flow, which is a deep neural net or a feed-forward neural net after that deep matrix or after that direct mapping to keep the comparison of possible. I'm showing you the cases of incorporating spatial autocorrelation using the spatial interpolation method first. So this is our prediction using the IDW plus DNN. This is our ground observation from individual distributed monitors on the ground. This is our ground truth, which is the satellite observation of tropospheric nitrogen dioxide in the same region. So we hope to find the relationship between this and use this to predict a field, a map that is matching very much towards our ground truth. So that is basically the process. So you can see that, especially in Los Angeles, we're dealing with Los Angeles regions. In many of my studies are dealing with Los Angeles region. So in this case, you're seeing that the spatial interpolation is treating two stations at very nearby location And the spatial interpolation is creating that discrepancy of predicting a very low number of nitrogen dioxide here, but a higher number of nitrogen dioxide later in the nearby location, which is not following the range of the general pattern of nitrogen dioxide. On the right-hand side, we're directly mapping, which is using a deep matrix network, directly mapping this distributed station with the fuel, with the map. And it is producing a better estimation, which is having a lower error. The third case is one of the recent cases of my study, which is to separate the impact of environmental factors. In this case, is wildfire smoke. So in most cases, when we're dealing with time series prediction, like a short-term prediction in the future, in wildfire-prone area, the problem is you can hardly differentiate wildfire smoke impact with general air pollution, general emission. So for one model, it is hard to predict in the correct magnitude when wildfire comes. When you train for the same area with wildfire cases and non-wildfire cases, the existing models are generally overestimating when there is no wildfire, but underestimating when there is wildfire. So it is really hard to identify or focus on the factors that is really making the major contribution to the PM 2.5 concentration on the ground. So in this case, we're doing that in a attention-based mechanism. And for people who know or don't know attention mechanism, the transformer model is the original the model that we focus on modifying. And attention mechanisms are really to focus on the relevant information instead of focusing on all information. So that's really helpful in our case. To further constrain the model to focus on wildfire smoke using wildfire smoke related variable and not focus on wildfire smoke, but other variables when there is baseline, when there is no wildfire smoke impacting this area. We're designing two things to be incorporated in the transformer model. One is to explicitly embed the spatial and temporal information and the value embedding, which is the other variables, the heterogeneous variable that we use, which are the wildfire location, the wildfire intensity, the smoke coverage. And we also incorporate other meteorological factors like wind speed, wind direction are really important. The traffic would be the baseline emission. So all these variables are embedded in the value embedding part. We also changed the attention mechanism of the original transformer into a sparse attention. So instead of focusing on all of these relevant information, we want to have the decision-making process a little bit more focused. So it's a sparse attention, only this relevant information that is really towards the decision-making in this time point are being incorporated. So let's take a look at the results when there is wildfire. The spatial temporal transformer model can help us identify the hotspot for predicting pollution when there is a wildfire. And this is the cases of 6 different stations in Los Angeles County when there is a large and long-term wildfire. So it is a combination of lake fire and range fire in 2020. Now you're seeing the 3 lines in terms of time series for every station. The blue one is the observation. The orange one is the spatial temporal transformer, which is the model that we developed. The green one is the transformer, which is the original transformer in 2017. You can see that when there is a big hit or the impact from the wildfire, the original transformer is underestimating the magnitude of PM 2.5, where the spatial temporal transformer is predicting, sometimes underestimating, but still in the same level of magnitude. You might want to ask, what about the days without wildfires? We noticed that when the days without wildfires, the original transformer tend to overestimate. That is the case we see in a lot of other recurrent neural network or time series predicting models. So in training one model, it is very easy to overestimate when there is no wildfire. So you can see the green line in the case without wildfire, it is still overestimating. The spatial temporal transformer is keeping in the same range of magnitude. One of the things related to attention-based mechanism is that it is really helpful in terms of giving us the model interpretation or explanation of model decision-making. So we noticed that in the attention matrix, you can, of course, visualize the attention matrix in many different ways. In this way, I am visualizing a station by station type of attention. So for one station, you kind of see what are the neighboring stations or not neighboring stations are influencing the decision-making. So in this case, it is influenced by itself. In the second case, it's influenced by several nearby stations. In the third case, it is influenced by all of the stations in my network. The other case is that when you see the wildfire comparing with non-wildfire cases, the wildfire cases are really focusing on the wildfire-related variables. So in this case, it is focusing on the inverse weighted distance of fire location. In the second case is the fire intensity, inverse weighted fire intensity, and the wind direction. The third case is the fire location and the fire intensity plus. The non-wildfire cases are focusing more on the non-wildfire variables by the model, explained by the model, or proved by the model. So the first case is really focusing on previous PM 2.5 value. The second case is focusing on mostly the temporal indicator. So this station is in the center of city of Los Angeles. So it's really having this diurnal pattern of PM 2.5, and none of the other variables are beating that diurnal pattern of PM 2.5. The third case is focusing more on the traffic and previous PM 2.5 combined. So this station is located very much towards the traffic emission. Another recent case is to study the wildfire dynamics. It's related to extreme weather, but not exactly. So it's extreme events, let's say. So one of the things that is hard to predict the wildfire dynamics or wildfire prediction, it is because all of these variables related to wildfire prediction or wildfire, the fire front, is the biophysical factors. And the biophysical factors are hard to quantify. So in most cases, you are getting the reanalysis data for all these biophysical factors like biomass, type of biomass, density of biomass, the previous burn records, wind speed, wind direction, the soil temperature, soil temperature, soil type, and moisture. All of these are hard to quantify. So the complex is, first of all, is due to the complexity of the biophysical factors. The second complexity is there's something called spotting effect, if you have never heard of it. So the spotting effect related to wildfire is really the long range spatial and temporal correlation, because the embers are really carrying the fire to distant areas. It's not really progressing from one location to the neighbor location, but it's having that long range effects. So it's called spotting effects. This study, we tried out a previously mentioned way, convex TM, but adding some attention to that. Based on the fact that we know there is this long transport of this ember spotting effect. So we want to see if there is some way in deep learning that can capture this global spatial relationship, this dynamic global relationship. So in the convex TM, we're trying to use the past 10 hour to predict the next hour's burned value. So the danger of that wildfire or the fire front, you can say. There are two cases that we try out. One is called pairwise attention. One is called patchwise attention. So patchwise attention is really similar to convolution. You can understand it as really as a convolution. So it has a footprint for it to focus on local and neighboring effects. But this pairwise attention is to have a global effect. So you kind of have a pairwise correlation between different grids and any grids in this spatial extent. So we try to find out the pairwise similarity within the grids and combine them into the convex TM, into the convolution mechanism in convex TM. So one of the results that we get is to see whether these two mechanisms of attention can help convex TM better predict fire front, which is the fire-only mechanism. So you can see that the error, these are the error bars. The errors are really saying that the pairwise convex TM is predicting fire better. Overall, which means all of the grids combined, you're seeing the the patchwise, which is the CNN-based patchwise attention convex TM is predicting better. The non-convex TM, non-attention-based convex TM is predicting better when there is no fire. But in this case, we're predicting, mostly hoping to predict the fire front, which is the most challenging task in this case. So we want to see that the lower error bar in the fire-only mechanism. The second thing that we, of course, explore is the attention, right? For any attention mechanism, you kind of had this attention matrix, and this is a different way of visualizing attention matrix. So you kind of see the different variables and their temporal effects to the decision-making of different models that we try. The non-attention, the pairwise attention, and patchwise attention. So for pairwise attention, you really see that a progression of all these variables tend to have a better influence or higher influence on the model prediction. The patchwise is having a more complex way. This one is actually helping us better explain why it is predicting overall better. This is to show the attention matrix in more of a map. So you can visually see whether the attention is capturing the same temporal dependence of all the inputs. We see that the pairwise attention mechanism is aligning very well with the input biophysical features. So it is capturing the biophysical features very good. So usually what these attention matrix attention-based models or any types of model explanation can help us is really to explain the process of decision-making. Right now, we're only focusing on seeing the correlations, basically the correlations, so who is most important in terms of the decision-making process, but we've never touched on the real process of making the decision. So that is something that we want to try out later on. But with the attention mechanisms, we can provide not just the prediction accuracy or the metrics of calculating how well you're predicting in the future, but also to capture some kind of interrelated biophysical factors in the process. So what would be things that are relevant to the entire study or the core of my study? It's to expand on finding out how to prepare for the era of extreme weather. So based on all the results or potential directions of studying, predicting, understanding extreme weather events, there are things that we need to understand better. So of course, the best solution to mitigate the effects of extreme weather is to stop the accumulation of greenhouse gases, but that's not the core of my research. There are measures, of course, to mitigate the effects of extreme heat or the effects of extreme weather. There are cases that on the slides that you can create some natural hazard early warning system. Some of my work are touching to that. You can increase shade coverage in urban areas that is related to extreme heat in urban areas. You can develop climate adaptive crops that is related to agriculture or sustainability of crops. There are sustaining insurance coverage that is highly related to wildfire smoke, because after wildfire smoke or after wildfire, smoke indoors is a huge problem. And the current insurance coverage is not touching anything related to indoor air pollution after the wildfire is burned. The increasing the availability of air conditioner, air filtration, or air purifier would be something related to the wildfire smoke effects. or investing in the climate resilient infrastructure, which is a broad or a far stretch from what I studied. But overall, it is really for us or for people who study extreme weather to prepare for the age of extreme weather. If you have any comments, suggestions, collaborating ideas, please let me know. Thank you.
Thank you, Dr. Yu. Yeah, this is a wonderful talk. I think now we can open the floor for question. I think there is one question from the chat. Yeah, you can check. Right. And I will also start.
Let me read the question. So the uniqueness of spatial analysis method, if it is all AI ML based. So the difference between, can I understand it as the difference between spatial analysis versus AI ML?
Yeah, Jerry, you can also speak if you want to further clarify.
Yes, because I'm a CS major, but I'm working in the geographic research field. That's my question.
Right. So how is spatial analysis using machine learning compared to machine learning itself, right?
So yes, I mean the traditional geographic research using 3 laws of geography. Yes.
3 laws? I didn't know
3 laws. The Topolus law.
Okay. Yeah.
Topolus law, the craving. Yeah, but I mean looks like the modern geographic researchers, they are using the ALML. So what makes the difference between the geographic researcher for the CS statistics researcher? That's my question. Yeah.
Yeah, thank you. I think it's a very general question in my understanding. So there are applications, of course, we apply deep learning models or machine learning models in our cases. There are other fields, for example, the industry of law, the industry of supply chain, the industry of a lot of things are using machine learning and AI in their analysis. And there are many different ways of framing the problems. And I think in this case, the framing of extreme weather studies is very important. The way that we understand in terms of the computer science way of understanding extreme weather events and the way in geographical science or geographical analysis that we understand extreme weather events are probably different. So we frame our problems, like if you think about that in a deep learning way, then what are the predictors? What are the predictants? How can you measure what are the metrics are you measuring their performance? These are completely different. In one case, let me raise one example. So if you are studying wildfire smoke, let's just using wildfire smoke as an example, the way that we try to predict better wildfire smoke is very different from just creating a set of variables and making sure it is predicting to one particular set of ground truth. There are many different ways of predicting smoke, and there are many products with different uncertainty of observing the smoke. All of these are constrained into one problem, which is how much we understand the science of smoke, how different products and how different methods are assessing these uncertainties. So I guess the framing of the problem would be very important. What is the advantage for researchers in geography compared to researcher in CS and math? I kind of answered the same
question. I think maybe we can back to the more talk-oriented question. Yeah, I think we can leave those open discussion because there will be no answers. Any other question related to Dr. Yu's talk?
I see Dr. Shu's question. There's always the question to GeoAI, what makes GeoAI distinctive when compared with AI ML? And what makes GeoAI distinctive when compared with general spatial analysis? That's a great question. I believe Dr. Gao and other people in the core GeoAI group might have other answers. So in the research that I demonstrated, I think GeoAI is different from the general AI ML based on that we try to incorporate spatial, temporal, and variable usually in an implicit way. I would not say in an explicit way, because implicit way is better for the model to capture. So the transformer case is really an implicit way of embedding spatial, temporal, and value, like the heterogeneous variable. And that is not a mainstream in AI ML or in general AI ML, but that is making my performance, making my understanding of the problem better. So my answer to your question is that when we focus on understanding the spatial temporal process or the dynamics, when we study these Earth system science problems using GeoAI, we have that answer through GeoAI.
I think Dr. Shi is making a comment. Yeah. Very good comment. Yeah, I think the next one is a question related to your talk. Maybe you can.
Yes. So as part of the complexity of studying extreme weather events, limited sample size, how have you been able to address this complexity in your research? Right. So limited sample size, it is especially obvious in the example of this case. So this is to predict a higher temporal variability of urban tropospheric nitrogen dioxide. So the limited sample size is based on the overpass of the satellite, which is Trabomi or Sentinel-5. And Sentinel-5 has a daily overpass. So the limitation of that is we only know in the afternoon what is the spatial pattern of nitrogen dioxide. We don't know the diurnal pattern. So in my case, I am generating the data. So to address this problem, you kind of either generate the data, synthesize the data. In this case, it's both generalizing and synthesizing other data sets that is as a proxy to create more estimation of phenomena. Okay.
Yeah, thank you, Manzhu. Actually, I have a related question. So why I didn't say other question, people can, also a good time to type your question, or you can also click the reaction, you can raise your hand and you can unmute yourself. So my question is related to, your research is actually to understanding the spatial temporal process of extreme weather event, or later you also focused on like the prediction. So my question is, I think, as you mentioned that we know that deep learning or machine learning model require the label data. So if it's for supervised learning, but when we talk about like extreme events or those, like we can also think like those anomalies, they actually rarely happen compared with like normal events. So which we may have more labels. So maybe could you comment about maybe like since your goal is to extreme events, which rarely happen compared to what we knew about normal, which is, I think, very interesting.
So usually when studying extreme weather events or extreme events, there is a matrix called return period, right? So when you heard about like a 100-year flood or a 100-year event, these are based on statistical analysis on quantifying only the 98th percentile of a matrix or 90th percentile of multiple compound metrics for compound flood, for example. These cases are getting more often as we see in the past 5 years, actually. So you can easily see a 100-year event happening in consecutive years. That's possible. In terms of flood, especially, you see different part of the world is experiencing 100-year event of flood. So I guess the limited sample size in terms of extreme cases or rare cases are not that rare now. So now the problem would be, how can you define a rare case if you're still using all of your historical available satellite observations starting from 1960, then you're probably having a similar statistical quantification of 98 percentile, right? So in the year to come, you are still probably quantify that event as a 100-year event. So I think the problem, or a upcoming challenge, is how can you define extreme weather?
Yeah,
and we'll probably see more of that coming.
Yeah. This is no issue in when we use deep learning for anomaly detection or extreme events.
Yeah.
It's very challenging. Yeah, I think I saw Dr. Luang's hands. Yeah, feel free.
Hi, thanks for such a wonderful talk, Dr. Yu. So my question is about your next steps for making your methods more accessible to other users. So I believe in for most geographers or those who are doing extreme research on extreme events or extreme weather, so probably they don't have the skill sets or computing powers to build the model and use your methods you developed. So do you have any plans to make your methods more accessible to a wider audience?
Yeah, that's a great question. For every model that I develop, I have a GitHub, but that doesn't help a lot. I know it. So yes. So to make things available or more accessible to people outside of my field, or more of a beginner into using advanced modeling, it is really, I think it's better to have some kind of a summer training or summer workshop that, for example, we can coordinate summer workshop like this. And Dr. Gao has already coordinated such workshop in training workshop already. So in that process, you can kind of force yourself to make every steps easily understandable instead of just posting your code, no matter how that is understandable. But the process would really push that boundary.
Yeah, thank you, Dr. Yu. This is great. Any other, maybe one last question, and before we end this? Okay, so I think yeah, if no, let's thank you, Dr. Manzhu Yu, again. I think yeah, I think we really enjoy your talk. And just to make announcement, so this webinar series will continue, but we'll take a 1 week break, and we'll see you all in 2 weeks. Yeah, so
thank you very much.
Yeah, thank you all. Bye bye.